Okay. So in the last lecture, we discussed graphical methods of um, dimensional synthesis of mechanisms, and in this lecture, we will discuss the analytical methods. And make note, whatever we discussed regarding Chebyshev spacing and so on, that operates equally well to both the classes of methods. So in analytical methods, the discussion actually, the analysis behind the task is not very big. So I am expecting that today's subject matter will become, over relatively soon. So we revisit the kinematic equations. So this figure and this equation we have seen earlier also. So you see, this is L1, this is L2, this is L3, this is L4, and based on that, with this angle and this angle denoted by theta 4, theta 2 and theta 4, we get the coordinates of A, which is this is 0 0, this is L1 0, right? So we get the coordinates of A as L2 cos theta 2, L2 sin theta 2, and the coordinates of B as L1 plus L4 cos theta 4 and L4 sin theta 4. And then we take the difference of these two position vectors and say that that should have the magnitude of L3. That is L3 square is equal to x1 minus x2 whole square plus y1 minus y2 whole square. Okay, so whichever you call x1. So if this is x1, then this is y1. Okay, so then we expand this as we have done earlier once, and we get this. And then for analysis, we organize this considering theta 4 as unknown and theta 2 as a known variable. Now those will be known, both theta 2 and theta 4, and their values will be given. Okay, and L1, L2, L3, L4 are actually unknown. So we therefore organize in such a manner that we club together unknowns and try to call their groups as unified unknowns. Okay. So first of all the four L1, L2, L3, L4 are not independent. It is the ratios which will be independent. So to get the equation in terms of ratios, overall we divide by this twice L2, L4 and then organize it like this. The cos theta 4 term we keep as one term, and that will be twice L1 L4 divided by twice L2 L4. Okay, so you will get L1 by L2. Call that K1. Then you get K1 cos theta 4 minus twice L1 L2 by twice L2 L4. Okay, so that will give you L2 gets over L1 by L4. So minus L1 by L4, call that K2. So minus K2 cos theta 2. And then on this side nothing will remain because we are dividing by twice L2 L4. So that we keep on the other side of the equation, that is throw it on this side, and that will leave only cos theta 2 minus theta 4. So leave it on the other side, and then this L3 square also you bring on this side, and then you will get L1 square plus L2 square plus L4 square minus L3 square divided by this. Okay, call it K3. Okay, so K3, fine. So this is the equation that you get. As it is a single equation in theta 2 and theta 4, in which when the link lengths were known, then basically you knew K1, K2, and K3, and therefore, given theta 2, you could determine theta 4. Now, K1, K2, K3 are actually not known. In the three independent ratios of these, we have got three groups, K1, K2, and K3, which is equivalent. Okay. So either you say that these are my unknowns, K1, K2, K3, or you say L1 by L4, L1 by L2, L1 by L3. These are my three unknowns. They are simply ratios. L1 by one of the other. So K3 actually you can organize. See, K1 is already L1 by L2. K2 is already L1 by L4. Okay. L1 by L3 is missing, but in lieu of that, this is given. So this you can organize like this. So if you call L1 by L2 as K1 and L1 by L4 as K2, then in terms of K1 and K2 and whatever else comes as ratio, if you organize, you can organize it like this. K1 K2 by 2 plus, so that is this, plus K2 by 2 K1 plus K1 by 2 K2 and minus K1 K2 by this. So you see, if you had called L1 by L3 as K4, then you can you can solve that K4 from here like this. And this is just a little elementary algebra. So I'm trying to impress upon you that if you can determine K1, K2, K3, then based on that, you can determine all three independent ratios, L1 by L2, L1 by L4, which are simply K1 and K2. And since you know those two, and K3 you know, so from that, you can determine the third independent ratio. And that will complete your mechanism design. So if you do three position synthesis, then those two pairs, okay, so this equation, this great equation, equation F, is called the Friedenstein equation. Okay, so Friedenstein was the name of the person on whose name this equation has been named. So with three sets of theta 2, theta 4 put in this, you get three linear equations in K1, K2, K3, which you solve. Okay, and solution of that will be particularly simple. In fact, you can do without writing complicated programs or without doing much trouble, even without calculator for quite some time. Of course, you have to have the cost values. If you subtract one of those three equations from the other two, then the other two will be simply in K1 and K2 because K3 will get eliminated. And two equations, two unknowns is just child's play, right? So you can solve that, and then whatever K1, K2 values you get, you put in one of the three originals, and you get K3 also. So solve for K1, K2, K3, and based on that, get these ratios, and your mechanism design is done. Okay. So that's it for 4R linkage. Now, slider crank also you can handle similarly. This also we have done earlier. So here you impose AP square as L3 square, where A is L2 cos theta 2, L2 sin theta 2, and P is S E, right? So that is why S and E here, and these two are coordinates of point A. And when you organize this, now here you see you don't get ratios because here, I mean, K1, K2, K3 are not ratios, they are things, okay, with linear dimension. The reason is that one linear dimension is involved in the variable itself, which you are actually supplying. Okay. Earlier both were theta 2, theta 4. So dimensionless quantities were supplied, both of them. Now one is dimensionless, theta 2, but the other has a linear dimension. So depending upon what comes in the coefficients, so K1, K2, K3 may have different dimensions. All of them will not be ratios. But anyway, by simplification, organization, you can put it in this manner. K1 S cos theta 2, which will come from the 2AB term of this square, where K1 will be twice L2. Understand that this term actually has been thrown on the other side. And then sin theta 2 term will come from here, 2EL2 negative. So on that side it is going, so it will become positive. So you see 2EL2. Okay. You see here K1S and K2 are of the same dimension because K1 is only this much, twice L2, and K2 is twice EL2. So E has a dimension of length. Okay. And the constant term except for this S. Okay. This S square actually. So because the S square will remain on the other side. S square is now known for all the positions. The remaining terms will basically be L3 square, and from this side L2 square will come, and from here E square also will come. And that is why it is L2 square plus E square minus L3 square. Fine. So you have got this equation. Again, you have got an equation in three unknown design parameters K1, K2, K3, which are these in terms of three design parameters L2, E, and L3. Fine. And this is easier actually because this is only on L2. This is then E and L2. This depends on all three. Fine. So then with three position synthesis, you insert the three pairs of values of theta 2 and S, and from that you get three linear equations in K1, K2, K3. Solve for them, and once you have K1, from here you directly get L2 as K1 by 2. From here, then you will get K2 by twice L2 as E. Okay, so K2 by K1 basically. And from here, L2 and E you have already found. So their squares you add. From that you subtract the K3 that you have got. That will be L3 square, and you have got L3. Fine. Now you will have an issue that this fellow must be positive. Otherwise, the design is not going to work. Okay. So you will find that that turns out to be positive. Okay. Then this is only for three position synthesis. What if the issue is more complicated? And this is only for function generation. So for path generation and motion generation problems, there is a little pre-processing involved to define and parameterize a representative error function, and that we discussed earlier. Okay. Based on that error function, you work out the Chebyshev accuracy points. Okay. Now, if one or more conditions, here all the three positions were given. Okay. If one or more conditions are replaced with derivative based conditions, the analytical method can handle them as easily as anything else. Okay. In fact, derivative conditions will become even simpler. For example, you try to differentiate this with respect to time, you will get K1 S dot cos theta 2 minus K1S sin theta 2 dot plus K2 cos theta 2 dot 0 equal to twice s dot. Okay. So this is again another equation in s theta 2 and the k's. In fact, one k will be missing. Okay. And theta 2 dot and s dot. But that's not a problem because if you are given derivative based condition, then theta 2 dot and s dot information will be in your hand. Similarly, higher derivative. So if you are given three conditions in theta 2 s pair or theta 2 dot s dot pair or whatever, you can put them everything in this. Finally, in k1, k2, k3, you will get linear equations only, and then solve as usual. So in analytical methods, you can handle this kind of derivative conditions also. Okay, and derivative conditions will become even easier because k3 will go immediately. You start differentiating. Other kinds of changes, for example, if you are talking about synthesis with more points, you say no, three position synthesis is not accurate enough for my purpose. I want better. So if you want better, then you recall initially we worked out that for 4-bar mechanism, actually there were 7 design parameters. The scale of the independent variable, the scale of the dependent variable, initial point, initial value of the independent variable, initial value of the dependent variable, and then the three mechanism related dimensions, either 3 dimensions or 3 dimension related ratios. For the case of 4-bar, where both input and output are angular, their dimension was not of significance, so it was the ratios. In the case of slider crank, in which the, I mean, one of the variables of the problem s itself is of linear dimension, so there it will not be ratios, but it will be 3 dimensions, L2, L3, and E. Okay. So whatever it is, there are basically 7 design parameters, including these. In order to keep our task easier, we actually chose these 4, so that we got in hand a 3-position synthesis. Now, if you want a better design, then we don't choose them. So with 4 to 7 conditions or positions, either 7 position, 4 position, 5 position, or you say that many conditions. The conditions may be on positions, velocities, accelerations, whatever, or combinations. Okay. So with 4 to 7 conditions or positions, one can drop one or more of these from the selected value list. Okay. So if there are 4 conditions, then you don't select this. You determine this also as part of design. If there are 5, then you don't select these 2, and so on. If there are 7, if you want to make a very accurate synthesis for the function or the path or the motion, then you say I don't select anything. I want to keep all 7, so I can satisfy 7 positions, 7 close by positions. Okay, and that will be great design. Okay. However, other than the 3-position synthesis, the moment you go for more than 3 positions or more than 3 conditions, that is when you stop selecting these, when you want to determine some of these also as part of the synthesis process, as part of the synthesis problem, then the resulting equations in K1, K2, K3, K4, I mean, these are in a way the R1, R2, R3, R4 as we listed. So in terms of these 7 design parameters, then the equations are no more linear. Equations will be non-linear, and you will have to do some, you know, dirty Newton-Raphson kind of look iterative solutions, which is done, which can be done. There is no problem. Now then, somebody says that I am not satisfied with even 7 conditions. I want a very good function, okay, more than 7 conditions, and I want to explore what best I can get. Okay, so with even more conditions, one that you say that with forward mechanisms, more than 7 conditions cannot be satisfied. We have seen this earlier. Okay. So we go for 6 bar mechanism, which has more design parameters. Okay. So more design choices. The analytical approach will be similar to whatever we have done. Okay. But it will be more involved. But it can be done. Another possibility is to explore the end of the possibility of 4 bar mechanism itself or 6 bar mechanism for that matter. And in that way of things, you can say that officially we are abandoning this equation solving approach and we are formulating the master error function in this manner. That is the function or path or motion that is wanted minus what is generated with a few proposed design parameters P1, P2, P3, P4, P5, P6, P7 or P8, P9, P10 also. Okay. In terms of that, whatever is the error at different points, we take those all those errors together and formulate the sum of their squares, and that we define as the master error function in terms of the design parameters, because we have taken all the positions that we could think of. Okay, 7, 10, 9, 20, whatever you like. Okay, so if you are looking for the function generation from theta 2 equal to 30 degrees to theta 2 equal to 150 degrees, in that you want to design a nice curve for theta 4 value. Okay, so you say that in intervals of these many intervals we are going to take, or these many Chebyshev points we are going to take, and then that many, say, 2 degrees, 2 degrees, 2 degrees separation. Okay, 20 points, or you ask for 20 Chebyshev points, Chebyshev accuracy points. Okay, get it, and say that at those positions, whatever are the errors, I want the sum of the squares of those errors to be minimized, and you can do it. Okay. So this is some problem which is solved. I mean, there are sophisticated ways of numerical programming which can do that, or do even better. You say we replace this summation by an integral, and basically these two mean fundamentally the same thing. Okay, and we minimize this, and there are sophisticated methods for doing this terrific problem also. Okay? So these kind of things are done, and it is actually not that difficult as it seems, but it is difficult enough. Okay? So this is what analytical methods have, and you have seen that so far as the power of analytical methods is concerned, that is actually limitless, because beyond the point up to which one can go by analytical processing, one has the numerical tools in one's hand which can be utilized, and computation can be done in the computer program. Okay? So that is the advantage. Now this is where our analytical methods for the time being ends. There are other detailed methods. Some of them are there in the book also, but we don't need to go into that. You have got enough flavor of that. However, since we have quite a bit of time left in hand, this lecture till now has not become sufficiently large. So I fulfill one little promise in a little way. that I made um, in the beginning of the course. In the beginning of the course, I said that if I get the time, then at the end, I will give you a little roundup of spatial mechanisms also. Okay, so we will not spend a separate lecture on that, but in some 15-20 minutes here itself, we cover that. Say, we should actually start from the Kurzbach equation of degrees of freedom. Now, initially, we discussed that there are several kinds of pairs that are in use: revolute, prismatic, screw pair or helical pair, and cylindrical pair, spherical pair, and planar pair. Planar pair we represented with E, but here I am representing that with P prime. Okay, so for the planar case, we worked out the equation, Kurzbach equation. This is spatial version also of that. Remember, in the planar version, we said that in a plane, a rigid body has 3 degrees of freedom, and removing one link, which is the frame, we have n minus 1 links. So 3 times n minus 1 is the total degrees of freedom the links have, from which pairs remove some relative freedoms. And for every revolute pair and every prismatic pair, we removed 2 freedoms, because in a plane, out of the 3 freedoms, it will remove 2 freedoms. Now here we have to start with not 3 degrees of freedom for every rigid body, but 6 degrees of freedom of every rigid body. Linear motion in XYZ and angular motion about XYZ directions. Okay, so 6 times n minus 1 minus every revolute pair will remove 5 constraints. Okay, because only one rotary freedom between the 2 links it will offer. So minus 5 into number of revolute pairs, minus 5 times number of prismatic pairs. Helical pair also has 1 freedom, that means 5 constraints. So minus 5 times h number of helical pairs. Cylindrical pairs have 2 degrees of freedom, so 4 constraints. So minus 4 times number of cylindrical pairs. Both spherical and planar pairs will offer 3 degrees of freedom, 3 degrees of relative freedom, so 3 degrees of constraint. So minus that many. Beyond all this, if there are some passive freedoms, okay, which do not contribute to the input-output relationship, just one segment of the mechanism is executing some motion freely, uncontrollable, uncontrolled, okay, without anything, without any crosstalk with the input-output relationships, then such passive freedoms also you have to remove, and this turns out to be the degrees of freedom of the mechanism. Alternatively, you could work it out as n minus j minus 1. See, I mean 6 times n minus 1 is there, and for every joint you remove j. Okay, that is for every pair that you remove from here, as if all the freedoms are gone, but then the freedoms which they offer you add like this. So 6 has been subtracted here. For these guys, 5 had to be subtracted, so you need to add 1. And that makes sense, because for that joint, Fi for revolute pair, prismatic pair, and helical pair will be 1 each, so that 1 gets added. For every cylindric pair, 2 will get added. For every spherical or planar pair, 3 will get added. Okay, minus the passive freedoms. Actually, here I wrote FR, here I wrote FP to settle that it's here. So fine, don't worry. Okay. So table for Fi, this we have earlier seen. The revolute, prismatic, helical have one freedom each, cylindrical has two, spherical and planar have three each. Okay, so that is here. So one freedom means five constraints. Okay, three freedoms means three constraints, and so on. There is another little interesting thing in spatial mechanisms, that in spatial mechanisms, to show position and orientation together, quite often we use this kind of a transformation matrix. Okay, so for every rigid body, we attach a frame of reference to that, and then say that frame of reference has a position and an orientation. Position is denoted, or position is represented by the position vector of its origin in the fixed frame, which is here P1, P2, P3. That is the position vector. And orientation, here comes the real, pain, because in planar motion, orientation or rotation could be represented with only one angle, theta. In 3D motion, orientation can be represented with three angles, but with a lot of headache. The complete description of orientation in a 3D scenario, 3D space, is basically by a matrix, which is an orthogonal matrix. In that orthogonal matrix, 3 by 3 orthogonal matrix. Okay? That 3 by 3 matrix is written here. So the first column of the 3 by 3 matrix will be the unit vector along the x-axis of that frame as expressed in the base frame. Okay? So base frame will have some orientation, and that body whose orientation you are trying to describe, that will have some other orientation, that frame. So that frame's unit x vector you take, and take its projections along these three xyz directions, and those projections you write here. Similarly, the projections of the y unit vector and z unit vector. So this is the rotation matrix. It is an orthogonal matrix. Three unit vectors mutually perpendicular with a right hand rule satisfied. Okay. When you write the orientation matrix or rotation matrix in this 3 by 3 manner, and the position vector after that in the fourth column, and then put a dummy row with 0, 0, 0, 1. Okay. In this manner, you can represent the position and orientation together of one frame in another. You say in frame I, you are describing frame J. This kind of transformation matrices are used to transform from one frame attached to one link to another frame attached to another link. And through this, the rigid body motions get easily represented by a matrix multiplication. Okay. So the way position and orientation can be represented with a matrix like this. Similarly, whatever actual rigid body motion will bring a body from a reference position to a current position will also be represented by the same transformation matrix. Okay. So from one frame to another, like that, you describe the kinematic equations with this kind of transformations, and this will represent rigid body motions, and this will also represent at the same time positions and orientations of one body with respect to another. Okay. So beyond this, we do not go into this at present. If you need to analyze spatial mechanisms, sometimes you will come across them and you will make good use of them. I should show you one example of a spatial mechanism. This mechanism is known as 3PRPS mechanism. Why 3PRPS mechanism? Because you see, this has a frame which is represented by these hashes, these hashes, and these hashes, and an output link, often called as platform in this context. Okay, and these two are connected through three legs. That is why three. And what kind of legs? The legs are prismatic, revolute, prismatic, spherical. Okay, all three of them: prismatic, revolute, prismatic, spherical. Similarly, prismatic, revolute, prismatic, spherical. Okay? And if you try to work out the degrees of freedom that this mechanism has, then how will you go about it? You will say how many links are there. So in each of the legs, you will have this slider, then this link rotating about this axis, 2 plus this slider, 3. So 3 in this leg, 3 in this leg, 3 in this leg, 9, and one platform, 10, and one frame, 11. Okay, 11 links are there. So put 11 here, and you have got 6 into 10, 60. How many pairs are there? One sliding pair, one revolute pair, another sliding pair, and a prismatic pair. Okay, and that is so in each of these three links. So try to see how many constraints are killed. So 5 constraints killed here. Five. How many freedoms are killed? How many constraints are imposed? So 5 freedoms are killed here, 5 here, 5 here. 15 killed. Okay, and 3 here. So 18 freedoms, 18 relative freedoms are killed in this leg. 18 here, 18 here. So 3 into 18, 54. 54 constraints gone. So this was 60 minus from here to here 54. Okay. So from here you club all the revolute prismatic. From here you get the spherical also. There is no cylindrical or planar pair in this. There is no passive freedoms either. Okay. So this is a 6 degree of freedom mechanism. And typically this mechanism is driven through the prismatic inputs. One jack here, another jack here, and similarly in other legs. Okay, and these revolute pairs and these spherical pairs will get adjusted. Their locations, their variable values will get adjusted because of the constraints of the mechanism. Now, if you try to do position kinematics, one very awkward thing is that here doing the position kinematics will not be very easy in terms of the joint variables. Like the earlier case where we took the joint variables theta 2, theta 4, theta 3, etc. as variables, and then we wrote the loop closure, and based on that we eliminated some variables, and whatever is the degree of freedom, that many variables survived as independent after putting the loop closure conditions. If you try to do that, then in this case it will be very difficult. So this kind of mechanisms are often found relatively easier, easy they are not in any case, relatively easier to analyze by going the top down. So you say that rather than expressing the output in terms of input, we will try to represent the inputs in terms of the output. Say, since we are talking about 6 degrees of freedom, that is, this platform has 6 degrees of freedom motion capability relative to the ground, relative to the frame. So we try to give this a transformation matrix of this kind. We say, suppose this platform is at a position and orientation, its frame of reference origin is in the base frame at XYZ position, and its orientation is represented by three angles alpha, beta, gamma. Alpha about x-axis and then beta about y-axis and then gamma about z-axis, or some such consistent notation, so that in terms of that alpha, beta, gamma, we get the orientation of the platform in this manner. Then in this manner, we will be able to express the position and orientation of this body. And then using that, we can get the position vectors of this, this, and this. And then we can say that whatever is the fixed point from here to this, that vector we get. Okay. If we take its components in certain directions, okay, in this direction, in this direction, and then we take the angular position. So from this point, we can describe the length of this, the angle turned by this, and the length of this. And by describing everything in terms of the position and orientation of this platform, what we really do is that three subchains are decoupled. We express this position, this orientation, and this position in terms of the platform position and orientation, this, for which we give symbols, totally oblivious of where the other legs are going. Okay, whatever are the values of their variables, and that reduces the complexity of the problem. Okay, and this can be done more or less reasonably well. And the loop closure is actually affected where, when we say that the same position and orientation of the platform that is used in describing this leg up to a point in the frame, and what is used in describing this leg up to one point in the frame, that basically is in a way loop closure. Okay, because from a point on the frame here to this, and then from there to another point in the frame closes the loop. So this mechanism actually has two independent loops. Okay, so we are supplying these things as the independent variable symbols. So we actually are developing one more artificial loop, and then by developing that, we are telling that now we write three loop closure equations, one along this, one along this, and one along this. So one artificial loop we produce by prescribing the position and orientation of this platform. Okay. So these are some of the basic issues which we use in handling general uh, spatial mechanisms. And two more small points I would like to raise with you today, which are not in the general perspective, but in terms of specific issues. One is even planar mechanisms have rigid bodies, which are actually as bodies, which are actually 3D bodies, right? Now, so they also should, in some way, fit in the spatial formula generally, in general cases, in general situations, because the 2D planar problem is actually embedded in actually 3D space. But if you take the 4 bar mechanism numbers here and put in this, then you will find that this is very, very awkward. 6 times 3, that is 6 into 3, 18, minus 5 times 4, 20. So you will find 18 minus 20, that is minus 2. Okay. So for the 4 bar mechanism, the degree of freedom should be actually minus 2. Okay. And that is very dangerous. And for a spatial mechanism, it will be indeed so. Now, in the case of planar mechanism, a very, very special thing happens, that the revolute axes of all the 4 pairs are parallel. Under that condition, under very special condition, that degree of freedom turns out to be 1. Okay. So you would notice this if you are working with a mechanism that is very old, dilapidated, so that some links have got warped and some axes have got a little cranky, and the axes are no more parallel, originally designed to be parallel, originally were parallel, but after some 37 years have passed, they are no more parallel because links have bent, warped, okay, twisted. So then you find that driving that becomes trouble. Okay. So input is, I mean, you try to rotate the input, nothing else rotates, and therefore this also cannot rotate, and it gets sound comes, right? So that happens because the axes are no more parallel. So in the case of planar mechanisms, the all the freedoms that we have been talking about for the last 14, 15 lectures, they are all very special because in the spatial embedding, all the revolute axes are parallel. And that is a very special condition. Under that only, we could use the all the planar formulae. Okay, this is one thing. Now, for spatial mechanism with only 4 links, 4 revolute pairs, it will not be, it will not have any freedom. In fact, it will be not only a structure, but it will be a statically indeterminate structure. The smallest that, I mean, the smallest linkage, the mechanism with only revolute pairs, closed chain mechanism with only revolute pairs that will have any freedom for the special case with only revolute pairs will be 7 links. Now put 7 links here. That means n minus 1 is 6. So 6 into 6, 36. Minus 5 into 7, 35. And that gives you 1 freedom. 36 minus 35. Okay. So that 7R closed loop linkage has just 1 degree of freedom. And doing the position kinematics of that is enormously difficult. Okay, in general. This is one thing. The other thing that I want to mention to you, is that the simplest spatial mechanism that you can think of actually is an RSSR mechanism. I'll show you. Throw away the third, this leg, remove that leg, cut off. Okay, take a scissors and cut off that leg completely. Lock this jack and lock this jack also. If you lock this joint jack, then the base comes here. That's the position of this becomes fixed. It does not slide along this line anymore. Then this revolute joint remains. And this jack also you have locked. So now you see after frame you have a revolute joint, then a spherical joint because this is now a rigid body. This jack you have locked permanently. So R, S, S. Similarly on the other leg, R, and again frame because this jack and this jack are locked. So that RSSR is the simplest kind of spatial mechanism. And if you try to put RSSR mechanism, actually in spatial mechanism parlance, RSSR mechanism is the true analog of our 4-bar mechanism. Okay, you give input to this revolute pair and get output here. Through this particular line, I am actually suggesting that RSSR mechanism has a single degree of freedom. But if we put it in this, then what we will get? There are 4 links, right? So 6 into 3, 18 minus 2 revolute pairs and 2 spherical pairs. So 6 into 3, 18 minus 10 minus 6. 18 minus 10 minus 6. 2 degrees of freedom remain. So indeed, RSSR mechanism has 2 degrees of freedom, but 1 degree of freedom is passive freedom. Okay. Remember, we have cut off this leg. So RSSR is only this, this, this. And we are trying to relate the input angular position to output angular position. And there is one passive freedom, freedom of this body, freedom of this link to rotate about this axis. Join the centers of the 2 spherical pairs. That will give you an axis about which this link can go on rotating without contributing in any way in the input-output relationship. So that is one extra passive freedom. If you remove that, then functional degree of freedom for the mechanism will remain only 1. So that is one very little mechanism through which one can start the study of spatial mechanisms. So I think for spatial mechanism, this much discussion is fine as a little introduction to you, on which later when you study actual spatial mechanisms in other courses, in other subjects, then you will get more acquainted. Okay. So we stop here and we'll meet again in the portal separately through the forum and other things. So now best wishes for your exams, and the exam of this course, the midterm exam of this course, we will handle sometime after the midterm exam period is over in the next week.